Good evening, ladies and gentlemen. Thank you very much for giving me voice. Today, I will be talking to a topic which is called of using magnetic fields, so magnetic electrolysis, to enhance water electrolysis. The water electrolysis, especially, is the splitting of water under electrons, and the trouble of electrons is that nowadays the great idea to enhance and make it suitable for hydrogen production is polyproton electron membranes or carbon electrolyte membranes, and these membranes are very important, but they are sensitive to deposits, fouling, and then they require often changing. And the scientists want to think about solution of these problems. One of the solutions is making this according to this is making and the using the new artificial neural network, they found that if we put some magnetic field, so the abbreviation magnetolysis, because every current produces a magnetic field, and they restored the method which was from 1984 and then unused because they thought to be too costly. In case of electrolysis, they after would should be the profitable, and this was proven. So it was proven to be used, and this occur that the work which I wanted to talk is prediction of hydrogen production by magnetic field effect water electrolysis using artificial neural network predictive model. The work is by Professor Sir Bashar Istirk from Nesehir University in Turkey. This is the article recently published in International Journal of Hydrogen Energy. And these show us that what is water electrolysis, and they wanted to achieve high efficiency hydrogen evolution of water split. For this case, they developed special magnetic field after modeling of the system by artificial neural network to estimate the effect input of parameters such as vector material, vector type, supplied power, surface area, temperature, and time on hydrogen production in different electrolysis systems. Thus, the model architecture was using Levenberg-Markov algorithm. This helps the predictive and this shows efficient use for the materials selected and it was tested them. Why is made? The hydrogen has high condensation and could be replacing of hydrocarbon in case of energy, and the combustion and formation without hydrocarbons would be also grateful for environment because it will reduce greatly carbon dioxide emission and greenhouse effect. And for hydrogen production causing alkaline, proton exchange membrane, solid oxide, alkaline anion exchange membrane. Water is reactant of water electrolysis and it is dissociated into hydrogen. At the catalytic reaction, ionic reaction and overall reaction work going on catalytic will produce hydrogen monoodic water and oxide. This is the case in here. There is, after the magnetic field, the charge of particle is the density and the Lorentz force on the bubbles form on the electrode. Effect of the electrode surface is either up or down according to right-hand rule. The magnitude is greatest when applied perpendicular to the applied current density or velocity of the moment charge species. The upward direction of Lorentz force accelerates the buoyancy of the bubbles to which two forces are added. The magnetic effect of the electrode is known as magnetohydrodynamic phenomena induced by Lorentz force. By easily separating the gas bubbles from the catalyst surface, the magnetohydrodynamic convection mass transfer can reduce the polarization resistance due to the bubble resistance. Bubbles are easily swept from the electrode surface, thereby increasing the hydrogen production rate. Considering the importance of diversity in the production of use, the design optimization would be here useful, beneficial. In addition, the most efficient part of hydrogen production process and the importance variables are critical for optimizing processes and increasing efficiency. In this case, two approaches are typically used to optimizing predicting results through model and conducting experience through trial and error. But modeling is much cheaper and faster than lump experience. Various approaches have been used to estimate the production rate and the optimal configuration parameters for the hydrogen production process. These systems are data-driven and examine existing relationship between input and output parameters in an attempt to identify the influences governing the process input. A completely data-driven system without prior knowledge of the events that govern the process. They consist of an input layer or the hidden layer assists of the network in establishing the complex relationship that exists between the input and output parameters. In recent years, has attracted much attention for predicting hydrogen production because it has many positive features, such as efficiency, generalization, and simplicity. The primary feature of using in hydrogen production of many processes elements associated with many couplings. These connections are distributed representations of input and output data without a single neuron carrying specific information. Despite increasing